Hello everyone. In this video, I'm going to be continuing the reactions that are going to be covered for exam 2. And I'm not going to go over every single reaction that is in the reaction sheet because some of them are just simply ones that you memorize and just store in your memory bank, whatever. Others, they have some understanding to it, and they're going to be the more emphasized ones that you need to be more careful about. So, continuing from last time, we're going to be starting off with nucleophilic aromatic substitution. And as you can see, there's two types. There is the addition-elimination reaction, and then there's elimination-addition. Okay? Um, and the key difference between these two has to do with with the groups that are on the ring. Okay? So just like any kind of nucleophilic reaction, you have to have a leaving group, right? The key difference here is that now we're doing this with the benzene ring as a substituent. And so typically, in the reactions that we've been doing so far, the benzene ring has been attacking other things that we've made into very good electrophiles. But in this case, we're making the benzene ring something that gets attacked. And we're performing some kind of nucleophilic substitution, but it's on an aromatic ring. Okay? So, and it's very very unique because on top of that, it's on a aryl position, which is a leaving group that is on an sp2 carbon. So it's a very very unique type of reaction, and it only works. So whenever we do the addition elimination, and I'll show you why it's addition elimination and why the other one is elimination addition. Addition elimination only works whenever you have at least one group that is ortho or para to the leaving group. So your leaving group has to be ortho or para to some withdrawing groups. And the withdrawing groups help facilitate the reaction and help allow the double bonds to move out of the way when you perform the nucleophilic attack. Okay, because the double bonds have to move somewhere when you come and attack with a nucleophile. You cannot just have them remaining there. They have to move, and then they move back. Okay, so we have a leaving group, a good leaving group. So chlorine, bromine, and then we have the withdrawing groups that are orthopara, and then we have a good nucleophile. So typically, we have OH, OR, amines, right? Um, those are the ones that you're going to be dealing with typically, and we're going to be using this reaction to add these kind of groups to the ring. So if you need to add a OCH3 group to the ring, you do a nucleophilic aromatic substitution. If you need to add an OH group, you do this. If you need to add an amino group, you could do this. There's another way, which you already learned, which is reducing a nitrate into an amine. Okay. Um, so anyways, let's try to show the mechanism. Okay. All right. So since my handwriting is typically pretty garbage, I'm just going to cheat, and I'm going to take a picture from the book, and I'm going to use that to demonstrate the reaction. Okay. So this is from the book, right? A lot of things are in the book. I just have to look for it. So here's the mechanism for nucleophilic, sorry, aromatic substitution, and this is the addition elimination. And as you can see, so addition elimination mechanism requires a strong electron withdrawing groups to stabilize a negatively charged sigma complex. Okay, so just saying we need these withdrawing groups to help resonate the movement of the pi bonds when it comes and attacks. Okay, um, and really, so what you have here is you have a leaving group, right? And your nucleophile always attacks at the carbon where the leaving group is. So first thing that happens is the nucleophile, so in this case it's OH minus, right? It comes, attacks the carbon that the chlorine is attached to, right? Then this pi bond, it moves, right? And here they demonstrate it in a two-step way where first it becomes a negative charge with a lone pair, and then, this is really what happens, where it resonates, it can resonate into the NO2 sigma bond, and then we can have this resonance structure over here. And then what happens is you have all these different, resonance structures. They're just showing, the negative charge moving throughout the molecule and stabilizing itself, right? Because that's what makes something stable. That's what, allows me to have reactions sometimes is the ability to delocalize a charge. And really what's happening here is that these withdrawing groups are facilitating the delocalization of a disrupted aromatic, um, you know, conjugated system. And so I'm taking this negative charge that is created, and I can resonate it throughout the ring. And most notably, I can resonate it into these withdrawing groups that increase my stability. And so this allows this to happen. And so, long story short, we can just stop at the first withdrawing group that's ortho to the leaving group. Okay, and then what happens is, this comes back, right? It resonates back, and it pushes these pi bonds back to form this double bond right here. And when it does that, it causes this two arrow, these two arrows. So this resonates back in, and it kicks off the leaving group to form this double bond again. And this is what we really get, right? This is our answer. Okay, and the last step, right? So this is our answer. This is our completed reaction. Okay, and what you'll see is occasionally you'll see two E. You always have to put two EQ, and occasionally you'll see a second step. Here it's not shown. Let me check my notes if I actually have that. But well, they actually don't have it. But I would be careful to see what she has on her keys sometimes, and see if she has this always. But usually second step you can have second step HCl plus, because in the case of whenever your nucleophile is OH or NH3, okay, when it adds to the molecule, especially OH, right, when it adds to the molecule, it becomes now an acid, right? And this acid is very acidic because it's attached to a structure that has lots of resonance, so obviously it can delocalize any negative charge, so it forms a very stable conjugate base. And so essentially, we have this product formed, but also in the presence of our original nucleophile or our base, essentially. And what they're showing is that this process right here will readily occur. And so what we do to make sure that we get the actual product that we want, we have a second step where we have H3O plus, and we make sure that we get our our phenyl. This is a phenyl. Phenyl is this. Okay, I'll have another video going over the names of important benzene structures that you need to know. All right, and so we want our phenyl. And so to make sure we have our phenyl, we have a second step that is just acidic conditions and make sure that it's protonated. Okay, and so that's addition elimination. Okay, so nucleophile attacks, then it resonates, then it comes back in, forms the aromatic structure, kicks off the leaving group, right? That's the function of the leaving group, it gets kicked off. And now we have a fully aromatic structure with our addition, our substitution. And that's all there is to it. The most important thing is that we need at least one, right, ortho para withdrawing group. The more you have, the better, right? More delocalization, the better, the more stable, the faster the reaction will progress. That's a fact question you need to be thinking about for later. All right, now let's look at the addition, the elimination addition, okay? And we'll see how it's a little bit different. Okay, so here is the elimination addition. So the first one was addition elimination, right? We added the nucleophile, and then I performed a elimination reaction as you saw, right? We eliminated. Well, let me just get this out of the way, right? So what we did over here, this is the elimination step, right? So the reformation of the double bond, okay? And so this one is elimination addition, where that happens first. And so what happens in this reaction, okay, so that if anyone can notice by now, what's the difference between this reaction and the last one? The key difference, if you can see, is that this one has no withdrawing groups on the benzene ring. So basically, we're trying to perform a nucleophilic aromatic substitution, but I don't have the withdrawing groups that allow me to delocalize that charge and make a stable structure. So what we have to do is, and this is not demonstrated here, they show it in other places, they're just showing a very simplistic version of the reaction. But you have to have your nucleophile to EQ, you have to have high heat and high pressure. Okay? So 350, whatever, here it's 340, I put 350. 350 degrees Celsius, 200, 2500 psi. So high heat, high pressure, and your nucleophile to EQ. And then obviously you have, if your nucleophile is something that forms an acidic product, then you have to have a second step H2O plus. Okay? So that's the difference here. Withdrawing groups, no withdrawing groups. And so this is done under high heat and high pressure. And so what happens first is your nucleophile, so your OH or your NH or whatever, comes and it deprotonates a hydrogen on a position that is adjacent to the leaving group carbon. So your leaving group is right here. We take either, this hydrogen or this hydrogen, whatever, that it has to be a hydrogen, deprotonates it, and I form a lone pair that is here. And what happens is this lone pair resonates inwards and it kicks off the leaving group and it forms this very important structure known as the benzene. Okay, and the function of the benzene is basically an electron acceptor. Okay, it's like it has its own resonance structure, and it can be attacked, and then one of these bonds can be pushed out, right? And so it allows this attack, and then this can be pushed out. And so what happens is you have this structure that's formed, and your nucleophile comes and can attack either from the top or the bottom, right? There's no difference to the top or the bottom, okay? And then it'll attach, and then you'll have this negative charge, and then all that would happen is that this negative charge is going to protonate, because now it's very basic, and then you're going to get your product. Okay, so this is our product right here. And obviously, if it's acidic, then you have to do another step of protonation, H plus, whatever, H3O plus. Okay, the difference between H plus and H3O plus is that this is non-aqueous, this is aqueous. There are conditions later where we have to be very careful about this. For now, just use H3O plus. Okay, so formation of the benzene, and then it gets attacked by your nucleophile. And then the nucleophile, has a structure that resonates outwards. You get this negative charge, and this negative charge protonates, and then you get your product. And that's what we have here. And then this bottom part is just demonstrating that you can get a mix of products because the benzene, it can be attacked on either side. So I can have my nucleophile attached over here or over here. In this case, this is a naked benzene ring, has no, we can't tell the difference between it attaching at one place over the other, but this one has a CH3 group. That's the only reason why there's a CH3 group here. Okay, it just so that we can see the relative arrangement of where this NH2 attached. So just for demonstration purposes, right? So I'm just going to use my program. Snipping tool is the lifesaver. Okay, so we have this, right? And so the benzene that would form from this would look like, so I have my CH3 group. Here's my CH3 group. All right, so I have that bond, and then the benzene would be like this. Okay, so it would be right here. And then obviously we can attack from right here or right here. And that's how you get either an attachment at the original location where the leaving group was, or the location that is directly to the right of it. Okay? And you may ask, but Eamon, how do you know that the benzene forms right here? How about to the left? Well, it has to form in the location where the pi bond is, and really, it just depends on, whatever resonance. I could have drawn it a different way, right? It doesn't really matter too much, right? Benzene is a circle. So just choose an orientation, it doesn't really matter, and then stick with it and just be consistent. But I really don't think you'll have a question on the exam where you have to like write both products, because there's a mix of products technically. But just for you to know that the benzene allows the attack from either the top of the from the one side and the other side. That's the most important thing. Okay. All right. Let's see. Let's see. Okay. All right. So that covers that reaction. So that's aromatic substitution, right? Nucleophilic substitution. Okay. Now let's go on to something else. So just going down the list. Now we have the Birch reduction. The Birch reduction is this is completely different. Birch reduction is just a way of reducing benzene rings um, to two double bonds and instead of three. So one of the double bonds inside the benzene ring is reduced, and we're left with two. And you have to use Na or Li, solid Na or Li, and you have to use liquid NH3 and any alcohol. Okay, so ROH. And what you see here is that this is withdrawing groups, these are donating groups. And whenever you reduce a ring with a withdrawing group, the withdrawing group is always excluded from the sp2 carbon, right? So it does not touch the double bonds. And then whenever you have a donating group, we want it to be on the double bonds, okay? And so now you may ask, well, what happens if I have a benzene ring that has both a withdrawing group and a donating group? Well, the rule is you always want to maximize the number of withdrawing groups that are not touching the double bonds. So your first goal is to fulfill this rule. Then, second goal is to fulfill this rule. This is more important, to have the withdrawing groups not touching the double bonds, okay? So that's just for later purposes when you're doing a question and you see multiple groups on there and you're not sure, your goal is to make sure the withdrawing group is not touching, okay? So that's that one. It's pretty basic. There is a mechanism for it, but you don't really have to. You don't have to really go over it. All right. Let's see. Really, these reactions are not too bad. It's test three reactions are the ones that are pretty bad, in my opinion. They can just be like everything has a long mechanism. These are just, you just need to be familiar enough with it and have some understanding. All right. So this one right here is the side chain reaction oxidation. So the oxidation of side chains of benzene rings, okay? And so whenever we put these into very oxidative conditions, so we have KMnO4 H2OH 100 degrees Celsius, and then you have this Jones-like condition where you have Na2Cr2O7 H2SO4 and heat, right? What this will do, it will oxidize any carbon that is directly attached to the benzene ring. So what it does, it oxidizes this position. Okay, it oxidizes this position, this position, this position, and essentially these groups get kicked off, and they are removed because the bond is severed, and so we're left with just carboxylic acids. So this carbon right here becomes fully oxidized, and that means we attach a carbonyl and they also have a OH group and forming the carboxylic acid. CO2H is this. This is CO2H, carboxylic acid. Okay, that's a full oxidation of a carbon on, that is part of any chain, right? The maximum oxidation of a carbon is obviously is CO2, right? Maximum of 4 bonds, everything is bonded to an oxygen. This is 2 bonds to an oxygen, another bond to an oxygen, and you have, your group, your chain. So this is, the maximum amount of oxidation on a carbon that is part of a chain or part of some other structure. Okay, and you'll see that anything works. This gets oxidized, this oxidized, this oxidized. The only thing that is not oxidized is very bulky groups that do not have any hydrogens on them. So this group is bulky and it is a quaternary carbon and it has no available hydrogens for oxidation. And neither does this one, so I guess I wouldn't use that logic, but just know that the T-butyl group will not get oxidized, okay? If you had a chain that was like this, and then you had at the end this would get oxidized still because the first carbon that is coming off of the benzene ring is still, that non-bulky. So the only thing that will not get oxidized is this T-butyl group, okay? So that's just the only thing you need to remember about this. bulky group will not get oxidized. And both these reactions do the same thing, by the way. They do the same thing. All right. Moving on. All right. So we have this. This is just halogenation of side chains. So the reactions that we all know, Cl2 and light, or Br2 and light, whatever. We always use Br2 and light. We usually never use Cl2 and light. You don't see that. Same thing though. And you also have MbS, which adds bromines to allylic positions. And so basically the takeaway for this is that whenever using these reactions, you will always brominate or chlorinate the benzylic position. Okay, the benzylic position is the carbon that is directly attached to the benzene ring. So as long as this carbon has hydrogens and it's the first attachment to the benzene ring, this will always be brominated or chlorinated first. Okay, and here they're saying pay attention to the temperature because they might be referring to the kinetic or thermal state reactions. But I don't think you will be dealing with that really. And the only thing that you need to be careful about is just that there's a small preference for using MbS and light whenever the ring is activated. So if the ring has a CH3 group on it or an OCH3 group or some donating group on it, it's preferred to use MbS and light on the ring rather than a Br2 and light. Okay, so nothing really complicated, just something to be familiar with. And then really the remaining reactions are pretty simple reactions. And I would continue looking over the remaining reactions that are on the reaction sheet. So right now I'm looking. Well, I guess I'll just show you. So we covered this, and the rest of it really is just review. So you have nucleophilic substitution of benzylic halides, and this is SN1, this is SN2, this is E2, basic things that you've seen before. This is just a very acidic phenyl ring, and with a strong base gives you obviously the deprotonated OH on the phenyl. This is a this reaction right here is a Fischer esterification. Yeah, they say that. And then the third reaction is no reaction because basically PBr3 is an SN2 like reaction, and you cannot perform that SN2 mechanism on a on an sp2 position. And then I wouldn't worry too much about the formation of salicylic acid unless she has it in her lecture notes. I've never seen this before. I don't know why it's even here, but I guess it was relevant once. This is important to know, although it looks very obscure, but the only thing is that she may use this reaction to form a dienophile, which she may use because you guys didn't finish the Diels-Alder from the last exam, so the Diels-Alder is going to be on this exam. She may use this reaction to form a dienophile, which this is, and then have your Diels-Alder reaction. So make sure you know this one. Make sure you know this. Okay. And the rest is just review. So this is review, this is review, this is review. And then from here, this is some new stuff, but I don't know if this is on your exam yet. I will figure out and I'll make video on it, but really your exam, as far as I know, only goes up till page 6. Okay, I'll make sure if it goes to page 7. If it does, no big deal. These aren't too bad. Okay, but yeah, that's it for this video, and good luck with your studying.